decarbonizing heating and cooling with district geothermal systems, state-of-the-art challenges and opportunities. And so that's in Golden, Colorado, which is right near Denver. And so I said, heck, if I'm out there, there's cool things going on in terms of some neat thermal projects that I've been wanting to see. And so I started making some phone calls and I got some help to put this together. So I just wanted to share some of my experiences with folks, because I think that you'll find it interesting. And I have to say, this is one of these presentations where I'm definitely not the expert at the stuff of the places that I went. Other people were the expert. Some of them might actually be joining. I see Carrie Smith is in town on this one. So if those folks that actually know more about these sites than I do want to chime in, that's great. We won't have time to go into detail about everything, but we will certainly want to be as accurate as we can in the time frame that we have. So I just shared my screen now. How's that? Can I make it? Did it go to the right screen? What do people see? Do you see something that says NREL?
Yes.
I love that. So this is the decarbonizing heating and cooling. That's what brought me out there. And that was on a Thursday. So I had a day before this, but just to give people a sense of what happened, I'm not going to go in any great detail, but it was a single track. It was about 25 or so DOE folks, NREL and other DOE agencies. And then there was about 25, what I'll say of folks that are outside of that. And so there was a series of workshops or series of panels, essentially. So exploring the role of district geothermal systems in decarbonization, and then, had a number of folks on there, deployment and challenges, exploring the benefits. And so I was on a panel on technology advances.
We're not supposed to burn it?
I think they didn't know exactly what to do with me, so they put me on that.
When you play with it, it's supposed to be burning.
Somebody in charge of zapping people.
Okay.
And so that was a full day, and that was nice. It was kind of neat to be, even though the NY-GEO conference certainly has its appeal, it was pleasant to have everybody in one room most of the time. We just had, one set of breakout sessions where we all split up, but for the most part, everybody was in the same room, and there was lots of good exchanges that went on. And that, like I say, was kind of the impetus to go. It ended up with kind of a draw on the whiteboard what some priorities might be, and then the DOE folks are going to sit around and try to figure out how that's going to turn into potentially or impact the development of programs and research priorities. So that was that one. Let me go to my presentation. So there's my great collage of things that I did, which you might have seen in the announcement. And so before that conference, I went and took a look at the Denver waste heat recovery setup there. This is sewer waste heat recovery. And then after, I went with Carrie Smith over to Colorado Mesa University. So that is that. And then I went to Vancouver, and I went to the Alexandra District Energy Utility, and was joined by MC Abbott, actually from National Grid, just happened to be in the area, which was fortuitous. And Constantino Reitz helped me out. He's the guy that runs that one. And then we went with the Shark folks, also in the Vancouver area, to a number of sites. And so I'm going to talk about that. And Michael Albertson helped put that together for us. Let me get on this. So I'm going to start with the Alexandra District Energy System. And this is, not the Alexandra, the National Western Center. It's really a sewage heat recovery system. And what they did is they dug a big wet well, and then they piped in about 2,500 gallons per minute. It's really of raw sewage. And then that has a pump that can handle solids that brings it in and ends up going into the system and being heat exchanged. And I have a whole bunch of pictures of that. And this is a district energy system. It's not just a domestic hot water recovery or something like that. This is then, after it goes through the heat exchanger, piped to a number of buildings in the area. And just, kind of a quick on that is that, so they've got the Shark unit that makes that interface, and then they've got heating and cooling that goes out through basically an ambient temperature loop, doesn't have antifreeze in it. It goes out to a number of buildings, and it's still in the process of being built out. So it has more capacity right now than is actually being utilized. And in things like this, which I'll show you in the photographs, they also have cooling towers and backup, really auxiliary or backup boilers, just to try to make sure that it's a secure utility. But let me get to the pictures. La, 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 there it is. So we start with kind of the ending. So
John, you're on mute for some reason.
have I been on mute this whole time?
You got up to, we'll start with the pictures.
Oh, great. Well, that's weird. I think John Rath muted me.
It was just a 5-second stop.
I'll take the blame.
He's just messing with me. No, it's okay. It's all right.
Guilty.
So this is Lynn Mueller, and he's the president of Shark. And that's me. That's Zainab Magabi from Heat. And, I just can't think of that guy's name right off the top of my head. But he's the guy that actually runs the plant there. So I'm just going to kind of flip through casually on these things. I'm okay to be interrupted. I don't know how many people we have on board. How many people are in the session?
John, we've got about 47 people. I'll try to moderate that and look for raised hands and things.
Yeah, and if you, I won't be good at monitoring the chat. So if you could take a look at that as well, that would be great.
You bet.
Okay. So there's the whole system, and one of the notable things is this big plate heat exchanger, which has very wide gaps so that it doesn't get clogged easily. And these little guys here, these little green guys, set it up so that it can reverse its flow every once in a while, just to make sure it doesn't get fouled up. And they've had real good success with that. But you'll get a feel for some of the components. This is they have a private company that operates it. And this is a woman from that, and she's just describing the system to us. These are the distribution pumps that go out to the district. They're not the ones that are pumping sewage. That's just Lynn talking about the whole thing. They've got, really slick interfaces where you can kind of see what all the data points are real time in terms of what's being pulled out of that wet well or sewage tank, as is listed there, and is being brought into the building. And just sort of, they have 2 Shark units, so they have 2 kind of in parallel to each other that feed into this very large heat exchanger. There's Carrie. Look at that. And then this is the wet well outside. So we were just inside that building there. And under here is where the sewage comes in to, basically, it's kind of, like a holding tank of sorts. And a number of these things are underground because that's where the sewage is, but I've also seen ones that are inside of buildings, kind of in big vats. And so because I was really curious, they opened it up. They weren't going to otherwise. So you'll see down there, this is about 25 feet deep, and they keep it at about 10 feet from the floor. That's pretty much, and so I think that's a common fill value right there. And there was a little bit of a smell there, but I have to say, one of the notable things about this and some of the other places I went with the Shark team is that there was no sewage odor at all inside the facility where the exchange is occurring. So it's really, if you want to jump in the wet well, you could have that experience, but otherwise you're pretty good. So there's a couple of pumps in here that pump out into the building. That's a really cool way that he hangs his phone that I'm going to start to adopt, but that's really not what I'm here to show you. I take a lot of specific pictures of pumps because I'm interested in pump sizes. but I'm just going to sort of shoot by a lot of those. They have a big bank of peak load boilers, as they say here. And like a lot of these systems that are future sized because they don't have their whole connected load on there yet, these guys barely run and are likely excessive and I think can supply a full backup. But the goal would be not to use those too much. Again, the peak load boilers, and those are big condensing boilers. Again, some of the distribution piping. That's behind the boilers. They also have cooling towers. So if a distributed heat pump system, for a lot of you that know, can be a boiler cooling tower. So in fact, if the sewage didn't work at all, the boilers and the cooling towers can carry the day. The sewage is a less resource intensive way to go, sort of renewable thermal. So we want to avoid that, but they do and can use these two big cooling towers that are out here. And that way the system kind of has auxiliary and backup sources. These are heat exchangers that look a lot like the ones for the Shark system, but they're the heat exchangers for the cooling towers outside, not for, see, peak load heat exchangers. So those are heat exchangers if the loop gets too hot. So in all of these systems, there's typically kind of turn on, turn off temperatures. And so if the distribution loop to the buildings gets too hot, you're going to start to turn on, one or more of these cooling towers. And if it gets too cold, you might turn on a boiler. But you're hoping that the waste heat recovery through the Shark system will carry the vast majority of the hours. So that's just a big, large gap plate heat exchanger. And the goal of any of these systems is not to have to take that baby apart and clean it very often. And like I say, with the reversing flow and some of the amount that they pulverize essentially the solids, they've had really good luck not having to open up heat exchangers on their systems. And so they are relatively low in maintenance. You still have to maintain them. So that was about, I think the thing that was notable about that in my mind was that essentially, if you look at this picture here, so we were out at that wet well, so we opened that thing up. So you have that, you got a big vat, you got a big storage thing, and then it comes in here, and there's a couple of these. There's two of these in a line here, but the footprint is kind of what you see right there, and that's about 1,500 tons of capacity. It's not exactly borehole capacity because it has a different kind of quality to it. It's a one-pass system that the energy comes in. You either put energy in the sewage or take energy out of the sewage. But it is about, it's somewhat the equivalent of 1,500 tons of capacity, which would be a vast number of boreholes or a large number of boreholes. And especially something like this in combination with boreholes, as we do larger and larger systems, it seems quite evident to me that we really need to look at our city and try to figure out where we can put these resources, because they offer a real balancing to a closed loop system. The closed loop system, over time could trend hot, could trend cold. And something like this is the type of capacity that could help levelize that and eliminate the need for as much closed loop thermal infrastructure. And at the same time, try to keep your temperature bands in a relatively narrow range. So it was, sort of striking that the footprint of that and the amount of capacity for that flow rate. And this is 2,500 gallons, something like that. We have flows in Albany and on a project that I'm working with, along with the Gray Edge Group and CHA Consulting, we have 4,000 gallons. So we got a much higher flow rate actually than this has. So it just really kind of opens your eyes to the opportunity. So then I went to Colorado Mesa University, and let me, as I told Carrie, it's on my bucket list.
John, I'm going to ask you any questions you've got for me, you might want to ask right away. I have to run off to a call for CMU. Kent Marshall wants to talk to us. So
I'm glad you're here. Thanks for coming.
Well, I'll try to come back if he's short.
I stole this slide from Heat from something I was on yesterday. And maybe you could look at it quickly if you can see, and you can tell me if it's accurate. So it talks about a payback, about $1 million in energy savings, big reduction in CO2, big cut in water usage.
The energy savings now is 1.8 million.
Okay, we'll have to update
with
that.
expansions and tuning. It's greater than Weber State, which is
Yeah.
interesting. And stuff, but now that they've got some proper accounting and some other ways of looking at it, they're saying it's 1.8. So,
Well, good. And so, and one of the things that I think is really, really great, in particular about this is, there's been a study that was done by Xcel Energy, which is a big utility out there, to try to verify some of the operating parameters, and they really have verified that the really stunning kind of COPs that you see here, or in that range that you get, have actually been verified by a third party. So I think that there's really, as we have thought for a long time, there's really something here, and something that we've all been learning from, and need to continue to learn from. And one of the things that was kind of fun, and this is this isn't specifically from the Colorado Mesa, but this is something Grage put together, but has a lot of basis on that, is they do have distributed heat pumps in buildings where the buildings are sharing energy with themselves. They're trying to keep that ambient temperature loop that connects all the buildings within a certain range as the buildings feed in and out of it. If they need to, they can then, activate the bore fields, of course, and that's going to help keep things level. And they've got bore fields in a number of different places. And then they have auxiliary sources like cooling towers and boilers, but those don't run very often. And then they also have irrigation heat recovery, which I can show you some pictures of, which is just a really cool feature. That's us. Yeah. Yeah. Look, and that's an air eliminator, which I just think is so fun, because I play with little baby versions of those on the systems that I'm I just figured any air eliminator that's taller than me is pretty big. We drove out there together, which was fun, and it's a beautiful place, and there's lots of pumps and pipes. And so the main loop pipe on this is an 18-inch, if I have that right. And then there's another area that I believe is 12-inch. It's a single pipe ambient temperature loop system. And it's got a couple of areas where and one of the big emphasis that it's HDPE out in the field. And Carrie had told me that they worked with a big irrigation company to do a lot of the loop piping, because they're accustomed to doing large HDPE systems. And so they were a great contractor to work with on some of that external work. The internal goes to steel. That was a common theme that I saw in some of these big systems. You got the big HDP out in the field. That's that air eliminator without us standing in front of it. It looks fake, honestly. It looks like something from like a carnival. This is the pumping system within this building that goes to the loops within the building. So this mechanical room has both some central pumping, and then also has pumping just for that building. So here's some of the central loop pumps. And one of the things that again is striking every time that you talk to Carrie and the Grage group guys about this, is their emphasis on trying to keep pumping energy low, and just really trying to work the system and understand the system, and keep it within temperature ranges, but with minimal pumping power. And a lot of that just happens through design, of course. The size of the pipes have a lot to do with that. And then the way that all the components feed into it, and the management of those. Again, I'm not expert on it, but that's why you get those phenomenally good COPs, because you don't have that parasitic load is as low as it just about possibly can be. That's a ground loop. Well, you can't see it. I always ask where valves are every time we'd come topside, and the valves are really cool here because they made them up, and they're have GEO on them. I asked if I could take one, and he said I couldn't, but maybe if I asked nicely. Here are some distribution pumps in other buildings. So I'm just going to kind of flip through just to show you some of the mechanical systems. There is a little vault down here, but there's a lot of this stuff is accessible in mechanical rooms. It's certainly not vault intensive. They do have cooling towers in some areas, and so as we go through here, you know, that's it says glycol refill. If it's for a cooling tower, then it might have glycol in it, but the main loop does not have glycol in it as it distributes to the campus, and they've managed that, and that's a real highlight for them is not to have to manage a large distributed glycol system. But when you have a cooling tower and the cooling tower is on a roof, you might have glycol on the outdoor side of it. Take lots of pictures of pumps. This is for me. I've seen this image any number of times on slides, but it was fun to actually be in where they're controlling it. And that's Carrie? Are you still around? Did I lose you? I did. And here's just, you know, some of the on-off set points to, you know, for if they want to start to start some of the different elements. These are the different temperatures that are going to turn on cooling towers or turn on ground loops. And all of that is manipulatable right from that screen. And it was kind of fun with the two of them talking. They're still learning about how to make it better. It's already very, very good, but they're always working on trying to figure out ways to make it better. There's another monster air eliminator. Why not? And another central pumping station here. And so they've got 3 pumps. Oftentimes that way you can run a couple at a time. You could afford to lose one. In a lot of conditions, one of these pumps could run the system from that mechanical room. So there's a fair amount of redundancy that they have built into it as well. I like to get pumping and pipe sizes. This is just a multi-stack, just another heat pump. Again, when you see this, it's almost always a cooling tower because they don't have isolating heat exchangers for buildings, and they don't have glycol in their main system. But the cooling towers have glycol, so you need heat exchangers on those so that it doesn't mix. And they did a little bit. This is a domestic hot water system that was in one of the buildings. We did then go out to, and this is where the irrigation system comes into this. It's kind of like a utility shed. It looked like there's a loop field, and the loop field comes in here. So this is the manifold for the loop field, and you'll see the PT ports down there for those of you that look for stuff like that. And I'm going to get to the other side. You know, lots of good purge ports and things. And so they've got this cooling tower that's out here, and essentially they use this cooling tower sometimes to lower the main loop, and then they also have an irrigation system that feeds into that same area. And so the irrigation system, when the water is running, I don't really have a great picture of it, but this is some of the irrigation piping. They basically are bypassing the cooling tower when the irrigation system. So the irrigation system is cooling the ground loop instead of the cooling tower, which is a savings on water and chemicals and maintenance and all of that. And you need to water your fields anyway, so why not? So just some, you know, good hometown basic. How do we do a big system? And it's definitely one to see for those of you that are interested in such things. So that was it for my Denver excursions. Then I went to the Alexandra District Energy Utility, which is a big 2-pipe system that was put together, and the foundation of it was in 2000 and I want to say 12, maybe 8, a while ago. And so it's so a two pipe distribution system. You'll see there's two big pipes down in the trenches there. And then they have a 22-inch mains, and then they're running, you know, 8 to 12-inch service lines. And the reason the service lines, which would be connections to buildings, are so large is because they really, as I found out when I was there, they mostly connect to very large buildings. They're not really tapping off of this main just for a bunch of single family homes. So let me show you some of those photographs as well. And MC joined me from National Grid. Okay. It's one of these. I know it is. Oh, that's the one. One of the main reasons I went to this one is because this group has been running this for a long time. They've got this Alexander District Energy Utility. They've got their bylaws, and in their bylaws, which is a relatively accessible document, they have the way that they bill for service. And I just thought that that was really cool. And I wanted to get a feel for it, but they bill based on BTUs. It's a combination of, just I can put my finger on it quickly. It's a combination of square footage and BTU usage. And since so many utilities and different folks in New York State are very curious about how we're going to bill for service, there it is. It's right at the end. I thought it was. So you'll see that they've updated these bylaws. And just recently, in the most recent update, they put an excess demand fee. So they've got the capacity charge, which is based on a square footage basis, and then they have a volumetric charge, which is per megawatt hour, and that's where they actually measure the BTUs in the connection where they make to the building. But then they also have this demand charge that they built in, and so I just want to know how people are doing that. I'm not sure, I'm not convinced that the way they do it is the only way to do it, but it's a way to do it, and that's the happy people. See, I am pretty happy. So I'm just going to flip again. This is mostly just a bunch of big pipes. I don't know if any of you do big systems, but this is a pot feeder. So if you want to add chemicals to the system, there's a place to do that. Their loop pumps are really big. And why are they really big? Part of the reason is because a two-pipe system does require quite a bit more pumping energy. It has an advantage in some ways because you can pump it right through into buildings or into the building heat exchangers without a secondary pump or a service line pump in the building. But that means the central plant has to take all of that on, and it has to go through two really big pipes when it distributes out. So these are the central loop pumps that go out. This is one of the BTU meters, and the BTU meters, which I found there's two. There's these Camstrup, and then there's Hauser and something or other. You'll see in a minute. There's two different types they use, but these are really only as good as the flow and temperature sensors that are connected to them. They are not a packaged thing with flow and temperature and the calculations. They're separate from that. Big pumps and pipes. This is just outside of the pump station that goes out to the utility, and here's where the cooling tower is, and then back here is actually where we pump right out. So they've got a couple of cooling towers. They say they run those maybe 4 weeks out of the year. They also have more capacity to put on, and when they originally did this, they didn't plan on being 100% renewable. So they planned on 25% of the energy would come from maybe the cooling towers in the summertime and maybe boilers in the wintertime. They're kind of rethinking that now, but they do use a little bit of cooling tower. These are two distribution pipes that go out to buildings, and these are the HDPE as it comes up through here, and this is the interface where it goes to steel. And again, for a lot of us, those are bigger pipes than most of us play with. Those are bigger valves than most of us play with. That is my engineer, Constantino. They've got a couple of vaults over here. They've got two closed loop systems. And see if I think I might be able to grab a quick picture of that. So this is from the materials that they have, and you'll see, the installation of the two pipe system going in right there, which is a long time ago now. But they've got, they just show one ground loop here. They put another one in since. So they've got two vertical bore fields that feed into this central plant that we're inside of. Come back. And then there's, those are vaults under there where the manifolds are for those. They do have a room that has boilers, and again, those boilers don't run that much, but they do run. So when the loop falls below a certain temperature, those will turn on just to modulate things. They're very much auxiliary. These two are stubbed out to a future loop field that they plan on putting outside here. So there's nothing connected to those now, but they did stub through to do that for the future. This, by the way, is a baffle for fresh air for the boiler. So when the boilers turn on, the makeup air for the boilers, and that's kind of common in a boiler room. Here's the that goes out, that connects to that manifold out there. So this is where the ground loop comes in another building. And then these are the ground loop pumps. And so right here, with the ground loop pumps, the cooling towers are right behind here. And then the first room we were in is in front of that. So there's kind of three different sections to this central plant. And these are insulated because they get cold. The ground loop will start, this is a glycol system as well. So the combination of it being glycol and it being two pipe and it having heat exchangers does add a lot to the pumping energy. And I think a lot of folks, it's a reliable system. It has a lot of advantages. You have the same entering water temperature effectively to each building because everybody gets a shot at that supply first time. It's isolated, so that's great that it's isolated so that the buildings can't mess up the utility loop. But there is a penalty for these things. When we do put glycol in the system, and when we do go to that two pipe, we do crank up the central pumping energy, and the overall system COP will obviously suffer. So it's kind of pick your poison a little bit. It's a little easier certainly on a campus system, but certainly I know a lot of us that are working even in urban environments and with utilities would hope we could get away from glycol at some point if we think we can do that safely.
John, JR here, just want to let you know, probably another 7 or 8 minutes. Will that work?
Okay, yeah. And then we went into a building. It actually has natural gas in to it, but the natural gas service is relatively small for the size of this building. This is where the interface is in this building with the district energy supply. So that came from that central plant, but maybe this is, I don't know, a couple tenths of a mile away. And then goes through a plate heat exchanger, which is insulated here. And then the other side of that heat exchanger is the building loop. And so the building loop, and this is kind of the line of demarcation for the utility, is this room. This is the BTU meter for this interface for this building. And this is basically, again, getting information from a flow and a temperature sensor somewhere else. And it's the quality of this temperature sensor and this flow meter, which is a electromagnetic flow meter, really has everything to do. So Endress+Hauser is the and then Endress+Hauser I saw in a number of places that Shark systems use Endress+Hauser as well for their flow meters. So, and that's the kind of stuff I was really trying to get a good sense of while I was out there. This is the internal piping for the building. These are the pumps that go to all the heat pumps in that building. So this is on the building side, not the utility side of the system. These are what are called end of cycle valves. And so this is essentially they're able to, when the internal building, the way it's controlled, when the internal building water falls below a certain temperature, those valves open and allow the utility water to go in and warm that building water up. And then if it gets too high, they turn on, but they're shut off for a big band. And it's between literally 8 degrees C and 30 degrees C, which is, I think, like 85 degrees on the hot side and about 42 or something. So if it falls below 42 degrees Fahrenheit, the utility comes on, but then it won't come on again until it's up around 85. So there's long bands where the utility is not interacting with the building, and the building is either has very low load, or the building is basically sharing energy with itself and not reliant on the utility. And I think they were surprised. This is the in-building system. They were surprised at how big that band was and how little the buildings required in the distributed heat pump systems. Now, they did not put geo. Some of their things say water. So the building's just for scale. So this is the scale of building that we're talking about, and then this fills basically that block. So they're big buildings. So you can afford to spend many thousands of dollars on BTU metering because you're only going to one place. The tenants are actually just billed on a flat rate. And then they have these fancy ones where they put their Lulu Island Energy, which is the name of the energy company. So those are their customized ones. And it turns out pink is the color of geothermal. Who knew? There is a Walmart that's connected to it. That's my wife, Catherine. But they use air source heat pumps for it. And the utility owns those. Also, this Walmart is really, really different than the Walmarts I go into. They've got 4-pipe air handlers inside there that go from these big air source heat pumps that are owned by the district utility. They do have a heat exchanger interface with the ground loops, but they don't utilize it much at all, and it's really not set up to do that. I think they thought the Walmart would overwhelm the loop fields, and so they made it a separate system. It's still on the district utility because they own it, but not because it's connected. That's a liquor store that is not connected, but in the Walmart parking lot. They do have natural gas in that part of town still. I know, I'm low on time. I know. Let me see if I can get. Meow. There we go.
Give you another 3 minutes.
I'll take those 3 minutes. So there's a couple of different products from Shark. I went up to their factory and we looked at the Piranha is a product that is made specifically to make domestic hot water. It's typically in a large building. It receives the wastewater from that building. It extracts thermal energy. It actually has a heat pump that's a part of the Piranha system. It's not a separate thing. And then it would say preheat a domestic hot water system from that. They have a version that could also be connected to a ground loop and do some other things, but it's a sewage waste heat recovery, but it's mostly used in building applications, single large buildings. The Shark system, on the other hand, can be used for domestic hot water, but it's more often can be used in district systems. And this particular one was really cool, and it is a new construction development where these large buildings that are built and being built, there's going to be more of them, all channel their sewage into this room in one of the buildings. It's in the basement of this building. And then it goes into these tanks. And one of the things that I just thought was just the cat's ass is this thing they have on their website, which basically is the room that I was in. And you start over here, and the sewage comes in. It goes into this tank, and the solids fall out of it. And this is pumped directly into the sewer. But then the overflow for that fills this tank. So this is a much cleaner tank. It's not clean, but it's cleaner. And this is where the energy is pumped. The water is pumped to the Shark system right out of that. And then it goes over to the shark system, which then has this macerator, which just makes sure the particles are a certain size that can be managed by the heat exchanger. They've got one of those fancy flow meters here. They're going to spin down here to get some more solids out before it goes into this big plate heat exchanger. The big plate heat exchanger exchanges with a loop water that then goes to the buildings for their HVAC. So we're using so much sewage that we're using it as basically a central loop. And then they have the control, and then they've got the whole system here. And again, they have those little valves that set up the reverse heat exchanger flow to kind of clean things out. But again, another one of these fancy flow meters. So they also and if you go into this, you can just kind of walk around. They also have sewage flows from another area that come in that can add additional energy. And then here's the distribution piping and pumping out to the building. So this is the clean water that goes out to the buildings and is essentially the loop for it. One last thing I want to show you. Oh. And this won some big award, but I don't know what award it is. This is Falls Creek is it's really downtown. It's in the dense urban environment for Vancouver, and they had a shark system there that they're going to put in four of what is now 2. They're going to put in 4 total, and they talk in megawatts. Some great number of BTUs. Those crazy Canadians. But one of the things I think is really cool about this is that this feeds into a district energy system, and basically the sewage waste heat recovery is a big component of that system. And they're going to they have a way to charge for that energy. I need to find myself here. La, la, la.
Easy on the Canadian loonies, eh?
I love the Canadians, as long as
John,
they're not.
we've got a couple questions, so you gotta hustle here.
I have to hustle. The pressure is so great. Let me see what I want to show you. I thought this was interesting. This is a building, big building, and they store the sewage in this tank before they pump it to the domestic hot water piranha systems that are up on they're up on a kind of a scaffolding in this one. And then this also goes right to a heat pump. It's a shark system, but goes right to a Colmac heat pump to preheat domestic water. So that's me. And sort of the same basic connections. And this is the one that I just talked about that you can take your magical virtual tour of. All right, I am ready for questions.
Hey, John, can I suggest this? Bill has an announcement he wants to make, and while he's doing that, you can look at the chat, and I see that Matt Brubaker's got from SUNY Cortland's got a question right up top.
Okay,
So
let's just go with the questions.
Oh, okay. John, do you want to? I can read the question, or if you want to see it.
I see. Well, Matt can also just come off the magical mute, unless we don't like that.
He says 2,000 to 2,500 gallons per minute for the system source exchange. About how much real estate is this covering? Question mark. 5 million GSF, 20 million GSF.
Let me see. It's probably 60 feet by 30 feet in the building, but then you might want to put a building around it. So it's much.
No, John, sorry. Yeah. My question was basically, okay, you talked about the source being 20 or 2,000 to 2,500 GPM
Yeah.
of sewage flowing through that the plate and frame heat exchanger, right? So my question was, as the utility there and the Colorado site builds that out, how much square footage do they anticipate serving with that size of flow?
Yeah, so the quick answer is I don't know. I do know more that it's about 1,500 tons of capacity. So that would be more the way that I would think about it. So 1,500 tons of capacity. And then you could combine it with closed loop, ground loops. I mean, there's ways to expand the system as well. You're not sort of stuck with once you max that out. And then the auxiliary systems also have the ability to expand it, you know, especially, and a lot of these are cooling dominated areas. So you can still keep the boilers off and extend the range by using the cooling towers, which isn't perfect, but not terrible.
Hey, John, this is Michael. I don't know if you can hear me. You got me?
Yeah. Yeah.
Okay. So on the Denver project, the Shark system is providing a minimum of 55 to a maximum of 77 degree condenser water temperature to over 2 million square feet of multiple buildings within the first phase. And so the water source heat pump folks that are on the call understand the sweet spot of efficiency and operation on COP/EER between 55 and 77 degrees. So that is what is being accomplished.
There you go. There's a square footage for you. Okay. Could machine learning be used to optimize performance of the system? Such a Bob Wyman question. I think that's a suggestion. Yes, I bet it could. If I knew if I knew much of anything about machine learning. Could you please share a link to the rates in Alexandra? Sure, I can. And I've done that kind of thing lots, and I'll do that again. We have a list that comes out of this, John Rath.
I'm not sure. Let me ask Christine if she can answer that question.
I will provide the slides, and I'll also provide links to all the pictures. So if somebody asked that, Ron did.
Yeah, so we will post this on the Let's Talk link on the site with the recording, John's deck, and then any other links that would be appropriate.
Yeah, I've given out the links to all the photos to different, you know, there's individual links to each photo set, and then you can poke around on it if you want. Does it create any unusual maintenance problems if the cooling tower is only used if you, yeah, not unusual. But yeah, anything that lays dormant, you always are a little bit questioning whether it'll work at all. But in the case of Lulu Energy and Colorado, the sewage waste heat recovery in Colorado Mesa, I think they run enough, and as long as there's maintenance crews taking care of them, they're nothing terrible. Any additional links, anyone interested in the shark? So thanks, Mike. Okay, how'd I do?
I think you did wonderful, John. Thank you very much. And we still have time for Bill to make his announcement. So Bill, you get the final say here.
Okay, thank you. Just wanted to let folks know that we are in the process of setting up a committee to work for some legislation this year that has been up in the past, and we think there might be a better chance to get it passed this year. One is to have an exemption from sales tax in New York State for geothermal systems, and the other would increase the cap on the tax credit that we have. Currently, there's a 25% tax credit in New York State for geothermal, but it's capped at $5,000. And this would raise the cap to $10,000. And it would also make it refundable. So if you don't have a tax liability, that you could get that full $10,000 to help you pay off the system kind of right up front. And we're seeking volunteers to help on a committee to work on this. If you're interested, I don't know what to do at this point because we're kind of running out of time. If people could put it in the chat, I guess, if you're interested, then we'll get back in touch with you on it. Thank you.
Or if you've got my email, feel free to do that. Okay, final announcement is that we hope you'll join us in 2 weeks for our next Let's Talk. We'll send out an announcement and links like we always do. But for probably 20 minutes of that session, we're going to hear from the Con Ed geothermal team, if you didn't know they had one, and a rate that we think is going to be of interest, certainly to installers in the Con Ed territory, but also to other geothermal folks. So I hope you can tune in for that. Christine, did you have anything you wanted to say as we close?
So Jackie brought up a good point. So I think we're off a week on our personal calendars. So we'll circle back on that because we did confirm Con Ed for the 13th. But Jackie's right, we miscalculated on our weeks. So it should be October 6th. But either way, we're going to have Con Ed.
Okay, thanks. And thanks, Jackie. Well, folks, wishing you a great weekend. Thank you for joining us, John. Special thanks to you, and take pictures on your next trip. We'll have you back.
Yeah, it was fun. Thanks for listening. And thanks to Michael Alperson, Carrie Smith, Lynn Mueller, and Constantino Reitz for setting up all the tours, and Danny Mueller. I saw that Lynn was on just a bit ago. So hi, Lynn, if you're there.
Enjoy your weekend. Take care.
Thank you. Bye.
Thanks all.